Hello, hello, hello. Welcome back to another stream. Today is Sunday, the 19th of October. And with half term coming up, I have a bit of time this morning when I would normally be teaching. So I thought I'd go through some TMUA techniques since I know I've got a student coming back this week doing a bunch of TMUA stuff. So I thought I'd get at least one completely live solve that is fresh and unseen for me before I kind of get into that. So between now and the beginning of January, I've got three things going on. I'm going to be going through TMUA stuff, continue going through the ESAT material, because I know a bunch of you are still doing that in January. And I'll be doing Oxford and Cambridge, and in fact, Imperial interview techniques as well. So that'll keep us nice and occupied for the next few months. I'm also going to start getting a more regular streaming schedule, which I'm going to upload in advance so you know exactly when you can see those different things. And I imagine what's going to happen is I'll keep one sort of evening slot when people are out of school to do something more interactive, like interview techniques. And then my more live solve content, I'll continue doing during the day when people are less available. But it's one I think you can watch in replay rather than needing to necessarily be there live. So with that said, let me just get right into the TMUA. Because TMUA paper one is largely based on syllabus material. In fact, I'll get that up as well. There is a specification for the TMUA, which is exactly the same as it is for the ESAT. Let me see if I can find that real quick. I think that'd be a very good place to start. Specification. Yes, so that is where we'll begin. Entire screen. I've got things ready for the solve later, but yeah, bear with. So going through this is showing you absolutely everything you need to know in order to complete the TMUA. Paper one is much more based on syllabus material. It's just applying the skills that you know from your A-level studies. The questions are challenging, but they're kind of in hand. What I find is with my preparation, I'm doing a lot of work on paper two with people. So the mathematical reasoning is something that isn't necessarily what you're taught in class. And so that's where I need to come in and provide some extra techniques to help people make sense of things. So this includes two topics I want to cover before I do my solve, which is negation logic and necessary and sufficient logic, or if and only if. Any other specific techniques I'll go through as they come up in the paper. But in the meantime, I'll be, explaining this and then doing some paper solves. So I encourage you to go through this line by line, make sure you're really comfortable with everything in the syllabus. It lines out for you exactly what you need to know for all of the papers. You can go through this in your own time. This is readily available if you just search for TMUA specification. And this section 2 logic, they have less here, as you can see. But this is trickier. So if and only if statements, converse, and counterexamples. And it's mainly these two that I want to cover. Necessary and sufficient. Yeah, negate statements. So I think this is really best done with example. So let me get rid of that. I'm going to go over here. So you might see a question which looks like this, which looks really, really off-putting at first. But this is a classic negation logic. Now, for negation, the way I kind of teach this is, and bear in mind as well, my background, I came up through the sciences. So I ended up specializing in material science. I did math through the first 2 years of my university degree, but I didn't do pure math. And so you may find a different system from a different teacher or tutor, which explains it in a way that works better for you. But I'll just go through how I explain it to my students, and it seems to have been quite consistent. So I create a number line. And whenever I see negation, I just always write this number line to myself. Where at the bottom we have none are, And then up from that, we have at least one is. So let's consider for something being true. None are true. At least one is true. At least one isn't. So all but one. There's at least one for which it's not true. And then here, all are. Now, important to note as well as those extremes is you can also do the exact opposite. So the opposite of none are is all aren't. And the opposite of all are, I've just messed that up a little bit. So the opposite of all are is none aren't. And this number line is something I use to make sense of any negation thing. So first of all, you need to understand that to negate, you don't go to the opposite extreme. You go for the thing. Let me give you an example. So all rich people are happy. As a statement, for instance. What's the negation of this statement? All are is this guy. The negation is not the exact opposite. The negation is not no rich people are happy. You need to consider, if that's this, what is the everything else? And so if all are is only taking up this position at the very end of the number line, well, what statement would include all of the rest of the number line? And that would be at least one rich person is not happy. And that's how you use this number line. Which section of the number line is included by the statement? And how do I include the rest of the number line in the negation? So the opposite of that, just for completeness, for those who are visual, it means that the opposite of that, if I place my boundary there with all are on one side, on the other side we have at least one isn't. Or they might see write that instead as some rich people are unhappy, or there exists an unhappy rich person. Unhappy rich person. Okay, now instead, let's do a different example. So let's say there exists struggling to come up with an example off the top of my head, but there exists something. That means at least one thing for which that is true. So I can plant that. That is included in the statement. The only way to include the rest of the number line is to say none are. So the opposite of there exists something is to say none exist. And so you can see this is best demonstrated in practice. So I want to show you how I would use the number line to solve something like question 17 here. So considering question 17, what I would do is I would lay out every part of the problem in the language of this number line. So let me make sense of this. It is stapled if and only if. For every whole number a which is in S, which is all, and it is true, so it is true for all a. So for all a in S, and I'm going to write a colon. So for all a in S, there exists a prime factor a. So at least one prime factor is. In fact, let me expand this just to make sure there's enough room for me to complete this. So for all a in S, it is true that there exists a prime factor of a. So there exists at least one a. one prime factor, where it is true that, so where is, so you'll see all of these have an is or it is not, or true or false. So it is for all A and S, it is true that. In fact, I might write it this way. None are true, at least one is true, at least one isn't true, all are true. None are false, all are false. So maybe that'll help better. So for all A and S, it is true that there is at least one prime factor of A for which it is true that it divides at least one other number in F. Divides at least one other number. So I use these true or false and these colons to see how each part relates to each other part. So rewriting this in the language of the number line. For all A in S, it is true that there exists a prime factor of A where it does truly divide at least one other. And if we're going to negate that, we're going to have to negate it from the front. So if we want to not this statement or make the statement false, we need to negate each part of the statement one by one. So let's put a false in front of that or a not in front of that. Every time I see a false or a not in front of this colon, I am going to negate the part after the colon using my number line. So here, how am I going to negate this? What's the negation of all R? All R is here. The negation of that is at least one isn't. So I'm going to rewrite that there. So this part becomes at least one A in S is not. And that replaces this. Now I have a not or false before this colon. So what that not is going to do is it is going to negate the thing that comes after it. So how do I negate at least one is? At least one is covers all this part of the number line. So the negation of that is none are. So therefore, that is going to become there's at least one A in S where no prime factors divide at least one other number. So I'm going to start there and see if I can find that. So here, let's go through. What I'm seeing is for every number A, well, no, we're looking for at least one A. So let's get rid of the every number A's. Okay, there exists an A, that is at least one A. Such that there are no prime factors of A, good, and that is R, so that does not negate the thing afterwards. And so I get to keep it. So there exists an A such that there is no prime factor which divides not every other number, but at least one other number in T, and so the answer becomes F. In fact, I think there was a better example I could have picked. I'm going to quickly see if I can find that. I thought this was the right one, but let me, because I think, yeah, let me demonstrate this with another example if I can. So I'm going to stop sharing screen just so I can find that without sort of causing too much disruption. And in the meantime, yeah, you can scroll ahead because no one's watching this live. So I'll put it in the description when I found it, when I moved on to the next example. But I'm going to go to the TMUA past papers and look for other examples of that, because those are really, really tricky. And those are the ones that people, I think, find the most off-putting. So I know I have the 2018 open for a different example question. Ah, right. Okay, no, it's here. Perfect. Not too bad. So let's go back here. And we're going to apply the same negation logic on this question 12 of the 2018 paper 2. So I'm going to go through that same process and demonstrate how that worked. So clearing my old working. Drag myself back over. So all are false or all are not. So are, is, and true are the same. And I'm going to say are not or are false. And removing that for the number line. Okay, let's see how that applies to this question 12. Again, the first step here is to rewrite this statement in the logic of this number line. So for any positive n, so that's an all r. So for all n true that there is a positive k, at least one is, it exists. So at least one k is true. It is true that this random thing is not prime for any m. And we're going to negate the whole thing. So it is not true. What is the negation of all r? The opposite of that is at least one. Sorry, all r is over here. So the opposite of all r is at least one isn't. So at least one n is not. That not is going to negate the at least one k is. At least one k is here. That includes everything above. And so the negation of that becomes so again, that not negates the bit after it. Negating that gives you none r. So it is true that no k r. And none r means that this keeps the same. I don't have to flip what comes after this. So let me see if I can find that statement. Not for any k, that's all kr. Sorry, not for all nr. So that's covered. So it's not going to be these. So it's definitely going to be there is in n, at least one is. Any k, that's all r. Any k, at least one k is. There is, sorry, no, this is, there is a positive integer n and a k for which. So that again, this no kr is not included. And that is as expected because I've seen this question before. The way to handle that is not to panic, but to think, okay, this is why we have this alternative option in the number line. Get rid of this for a second. So here, no kr, well, let's rewrite that. No kr is the same as all k are not. And then we have a not in front of the colon, which means we now need to negate this final statement. The final statement was this is not prime for any m. So none are prime. Or is prime for no m. So the negation of being prime for no m, none are prime, is at least one is. So this thing is instead not prime. Sorry, the opposite of not being prime for any m is that it is prime for at least one m. So let me see if I can find that statement. So there exists an n. So it's not for any. There is a positive n, such that for any positive integer k, I'll just come back here as well because I need to change this up because I've negated the statement, so that got rid of the not. So instead of saying not that, I've replaced it with is this. So here, there is there is an n for any k. There is it which for it's not prime. No, it's where it is prime for at least one k. There exists an m for which this is prime. Bingo, it's f. So it's complicated to pick up, but it is a system that works. I'm open to obviously finding out if there's a system that works better for some of you and adopting that strategy and explaining it. But this is the strategy I've been using to explain it. And if you pick this up and try a few examples, it does work. Now, the other thing I wanted to get into before I did my run was necessary and sufficient logic. So if I just scroll down a little bit, necessary and sufficient logic. Oh, there was the good example. Yes, it was this example. Because this is a sort of very practical example that I think will make a lot of intuitive sense to people. But the idea behind this is if we want to find the relationship between A and B, we can consider the situation. The simplest situation is either A is true or A is false, and that leads to B being either true or false, for instance. Now, there are two important relationships. I'm going to draw a kind of Z pattern here and discuss what that means, where A is leading to these things. Now, if this is true, we can say certain things. You can see that here, if we start off on A being true, the only result is B being true. So that means if A, then B. We can also see from this that if B, the only way to arrive at B being false is for A to also be false. So not B, only if, not A. The only way to arrive at B being false is for A to also be false. So this only if that. And we can rewrite that in necessary and sufficient logic. So necessary means that this cause must be true in order to end up at the end result, but that something else can end there. And sufficient means if I start here, it is sufficient to end there, but something else. Let me show you what I mean. So here, A is sufficient for B. If I start at A being true, yep, I get to B being true. That is sufficient. That'll do. It may not be the only thing that makes it true. It may be that something else is not included, but if A is true, that's sufficient. Yeah, that gets me to B. It does the job. Whereas here I can say something is necessary. I can say A not being true is necessary for this B not being true. This must be true. I cannot get to this without this. So if I start at one start point, if a start point leads to only one end point, that is sufficiency, and you can say if A, then B. If one end point can only be arrived at by one start point, then we say that end point only if this start point, and that start point is necessary to arrive at the end point. I can show you what that means in the sort of a different relationship. So, in fact, let me scroll down and do the same thing for the relationship between A and B. We're going to do the same thing, true, false. And this time I'm not going to do a C, I'm going to do a reverse C. So where I have my start points at A and my end points at B. So in this particular situation, we can see that B, only if A, that end point can only be arrived at by that start point. So A is necessary for B. And I can say that if I start at A not being true, then I get B not being true. And so A not being true is sufficient for B not being true. So let me give you an example. Let's say the kind of example is something like drinking in a bar. How to check the ages of people who are drinking in a bar to make sure no one drinking is underage. So over 18. Okay, so this is it. Let's do this. So let's say it is true. The condition A is being over 18. So if you are over 18 or you are under 18. This would mean you were drinking. This would mean you are not drinking. All people under 18 are not drinking. And if you are over 18, some people are drinking and some people are not drinking. So this, what was previously very abstract, pure language, can start to make a lot more sense in this context. Let me drag this over, in fact, just to make sure. No, not that. Can I drag this across? Finding out. No, drag it, move it. No. I hate text so much, guys. All right, I'll just widen the screen. So putting this in the language of the example I gave, drinking, you are drinking only if you are over 18. Being over 18 is necessary to be drinking. And here, if you are under 18, then you are not drinking. Being under 18 is sufficient to conclude that you are not drinking. And every sentence I just said makes complete intuitive sense from your day-to-day life. And this is how to take that and apply that in a more pure logic that you can apply in this context of paper 2. if you being under 18 is sufficient to conclude you are not drinking. There is another way to not be drinking. You can still be over 18 and not be drinking, but to get to a place of not drinking, under 18 is sufficient. It gets you there. And then if you are to be drinking, it is necessary to be over 18. So let's apply that now to this question. Maybe not this question. There was a better question. Oh, with quadrilaterals. I thought I'd found it. Apologies. Should be better prepared. Let me see if I can find it quickly. Again, I'll have timestamps below so you can skip over this section where I'm looking for it. But there's a really good intuitive case with quadrilaterals that I want to use as my case study here. And it looked exactly like that question, which is why I thought I'd found it. Impression. Okay, nope. So I'm going to quickly cycle through and see if I can find the one I'm looking for. Not that, not the 2019 paper. Is it 2020? Yes. Okay. So I'll get that downloaded and put on a tab. I'll zoom in. Okay. Great. Let me get sharing again. And again, I'll fix all this in the timestamps. Okay. So let's use this logic on the question of these, because I think parallelograms make intuitive sense. Shapes are something you're fine with. So let's see how this applies here. And I'm going to just keep this general A, B, true, false logic, and we can impose the question onto it. So we have a parallelogram, PQRS. Labeled anti-clockwise. And we have these three statements. And which of these are sufficient to make it a square? Now remember, let's think about what sufficient means. Sufficient means if I start there, being under 18 is sufficient to conclude you are not drinking. If I start here, do I end? If I have this start point, does that only get me to the end point I want? So in other words, how does that apply here? For each of these statements, if I start here, do I end only at the parallelogram being a square? So let's consider these one by one. This statement 1 is not sufficient to conclude that you have a square because it could instead be a rhombus. If that statement is true, it's not enough. It is not sufficient to conclude that you have a square. For the second statement, if the diagonal intersects at right angles, again, that is not sufficient because that statement is also true of rhombuses. And for this one, if those two angles are equal, that is not sufficient rectangle. To be sufficient, if you have your start point, it can only arrive at the end point you want. I might scroll through and find, because I was here in 20. Let me try that on the question. No, that was really complicated logic, though. see if I can find another if and only if. I think that might be sufficient. And in the interest of time, I think I have to start the paper now anyway, just to make sure I can finish them both in time. So what I'm going to do is I'm going to start the clock. And I'm going to try and get both done. But in the interest of time, just in case something has to bail before my 2:30 session, I've got 2.5 hours, which is just enough time to finish both. But then maybe not enough time for marking and explanation. So what I'm going to try doing is, in fact, let me just get everything ready. I'm going to do the 2023 run. So I'm going to get rid of anything that isn't 2023 based. Okay, this is 2023. We're going to start on 2023 paper 2 because that's the harder one, the one where I think I need to do a bit more explaining. I'm not going to do split times in the way that I would do with the more time pressured paper, but it's important because this one it's 75 minutes for 20 questions, which isn't bad. So what I'm going to do is I'm just going to set a timer for 75 minutes. So which is 1 hour and 15 minutes. And then I'm going to get going. I'm not going to do anything too crazy in terms of exam technique, except to say that if I don't like a question, I'm just going to skip it to make sure there's a good flow to my paper, to make sure I have good sort of confidence and momentum building as I'm moving through. So I'm not going to let myself get stuck in the mud because that'll affect my mindset about how the paper is going. So I'll start the time. Given that that is that, what is the value of x? This looks fairly straightforward. You just do the math. So for question paper 2, question 1, if that is true, let's rationalize the denominators. So 1 over root x minus 6, and that's going to be, we're going to multiply this one by root x plus 6 over root x plus 6. Actually, no, we're not. What we're going to do is we're going to bring them to a common denominator, which is functionally going to be the same thing, but I'm going to call that root x plus 6 from the over root x minus 6, root x plus 6, minus, and I'm not going to make a sign error, so that's going to be root x minus 6 all over, and you can see I'm already anticipating what possible execution errors could be. I'm not going to make the small mistakes here. So here, bottom there, difference of 2 squares. So on the bottom is just going to be x minus 36 for both of these. On the top, we're going to have root x plus 6 minus root x plus 6, changing the sign there. All over that is equal to 3 over 11. These obviously cancel, so you're left with 12 over x minus 36. Do you know what? It actually helps if I share my screen, doesn't it? Sorry about that, guys. All right, so question 1. I'll give you some time to catch up. So I've got this question. I'm bringing them to a common denominator. So I multiply the first one by root x plus 6, top and bottom. I multiply the second one by root x minus 6 on top and bottom. I make sure that I don't get the signs confused when I do the minus 6 there. Cancel everything down. It's all equal to 3 over 11. Okay, you're back up to speed. Cross multiply for 132 is equal to 3x minus math 108. Add the 108 across. I'm pretty sure this is a non-calculator paper. Yeah, calculator is not permitted. Cool, so add that across. 240 is 3x, x is equal to 80, which is answer H. Okay. Question 2, let's evaluate. So this is going to be classic polynomial division. They're the same limits, so I can bring those together. And I'm going to square them out just to deal with the fraction. Okay, so I'm going to rewrite this. So the 9 and 16, I'm going to say that is x to the minus a half plus x to the half squared minus x to the minus a half minus x to the half squared dx. So again, integral from 9 to 16. I'm going to square this first one out. It's going to become, well, I'm actually going to do it the same. No, I'll do it in powers so I can better integrate it. That's going to be x to the minus 1 plus twice the middle 2 plus x from squaring that, that's squaring out the first bracket minus squaring out the second bracket. We're going to get a very similar thing. So it's going to be 1 over x minus 2 plus x. And when I cancel everything, those are going to cancel, those are going to cancel, and it's just going to be the integral of 4. So it's going to be 4x between 16 and 9. So I'm going to take the 4 out, and that's going to be 16 minus 9, which is obviously 7 times 4 is 28, which is f. So finding that way of simplifying it, the fact that they had the same limits means I could combine the two, and leaving it in powers would have helped me integrate if I'd been left with any powers to integrate. Okay. Which of the following is a counterexample? I'm going to zoom out just a bit so it all fits. Although the powers are not looking great. So no, I'll zoom back in so you can see the question. Yeah, consider this claim. For all positive real numbers x and y. Okay, so a counterexample to the claim has to, well, disprove it. So let's just try them out. Is this a counterexample? So in the first case, for question 3, root of 1 to the 16 is obviously 1. That's the left-hand side. Right-hand side is 1 to the 4, which is 1. So that is, it does work, so it doesn't disprove it. So that's wrong. So it will not be I. In the second case, the root of 2 to the 8 is equal to 2 to the 4 is equal to 4 squared, which is 16, is the left-hand side. Right-hand side, 2 to the root 8 is 2 to the 2 root 2, which is very much not true. Left-hand side does not equal right-hand side. And let's try case. So that is a counterexample that does not fit the statement. And then for claim 3, we have the root of 3 to the 4, which is 3 squared, which is 9, is the left-hand side. On the right-hand side, we have 3 squared is 9, which is not disproving it. So the counterexample is 2 only, which is C. Moving on. We have a classic proof question. This is a very common style in paper 2. First, is it correct? Well, let's see if it actually is true. Which is the largest number of consecutive odd integers that are all prime? Okay, let's go through it. Let's just see if everything follows. There are 2 consecutive odd integers that are prime. That there exists a case. The statement 1 is correct. Any 3 consecutive odd integers can be written in that form. That is true. N is... Okay, so this is a sort of proof by contradiction. So considering all the cases of n, so n is either 1 more, 1 less, or a multiple of 2. If n is 1 more than a multiple of 3, then n plus 2 is a multiple of 3. Yes, because if n... Okay, so basically n is either 3n plus 1, in which case 3m plus 1, in which case n plus 2 would be 3m plus 3, which is a multiple of 3. That is correct. If n is equal to 3m plus 2, then n minus 2 is a multiple of 3. That is correct. If n is equal to 3m, then it is a multiple of 3, which is not prime, unless n was equal to 3, but that would make this 1, which is not prime. 1, 3, 5 does not work. 1 is not prime. Oh, this will be interesting. Okay, I think 6 is not strictly speaking true because they haven't considered the case where, n is 3 itself, which is prime, and in which case the reason why it doesn't work is because n minus 2 is equal to 1. So it is a correct conclusion, but I think the attempt is incorrect and the error is in 6. So I am gonna say G and not be super confident on that, but that's my logic. So 5. Consider the two statements. All right, we got our necessary and sufficient. So now again, so let's consider the true and falseness of it all, and let's establish what the relationship is. So I'm going to do my little A's and B's of it. Okay, so either k is an integer multiple of pi, or that is not true. The integral from 0 to k of sine, it either equals 0 or it doesn't equal 0. Let's work out what's happening. First of all, okay, let's try and work out what arrives at these endpoints. So if the integral from 0 to k of sine 2k, let's actually perform this integral. So we integrate sine, we get minus cos. So that's going to be minus a half cos 2x, which does differentiate back down correctly. So I haven't got my signs wrong. So that would be minus a half cos of 2k. Well, I'll take the minus a half out. Cos 2k minus cos of 0, which is 1. So that would be minus, yeah, I think that'll work. Okay, so when is this equal to 0? This is equal to 0 when cos 2k minus 1 equals 0. So when cos of 2k equals 1, this happens when 2k is, and if I draw my cos graph, n pi. So actually, when k is n pi over 2, it should work. So when k is n pi over 2, 2x. So in other words, as well, I know I'm going to integrate over half number whole wavelength. So the whole wavelength would be pi. So yeah, it should be pi over 2. Every pi over 2, it'll work. So it means certainly that when k is n pi, it is true that that integral is 0. However, it is also the case that when it's not equal to a whole number, that I can get equal to 0. And it is also true if this was something random, I would get something not equal to 0. So I have this case. That is my relationship of start points and end points. So what does that mean? It means if that, then that. So this is sufficient. So R is sufficient for K, but it is not necessary. So it is sufficient but not necessary, and that makes it C. And that's how you can use this technique that I went through earlier. Because there are other ways of arriving at that. So it is not necessary, but it is sufficient. If I start there, I do end there. It's sufficient if I, yeah. Okay, question 6. Come on. Okay. So trying up 6. A is a real number and A is bigger than 1. Which of the following equations must have the same number of real solutions? This is not gonna be fun. Oh, I'll tell you what though, we could sketch these because we know because A is bigger than 1, that's going to be an exponential curve. And we know line 1 equals x is going to do that, and it could intersect at 0, 1, or 2 places. Well, A, it's not true that, hold on. Okay, so let's go through them. Well, that statement one is a complete rearrangement. And it also works because log a of x is the inverse of log a of x. And to take the inverse of a function, you reflect it in the line y equals x anyway. So the line y equals x will be unaffected in that reflection. And then that will have the same number of points of intersection. One is just true for that reason and the reason that if I take logs of both sides, I would get, if I take log to base a of both sides, I get x on the left-hand side and log a of x on the right-hand side. So that is a rearrangement. I think one is definitely correct. The statement 2 comes about from squaring both sides of the equation, but I know that squaring both sides of the equation does not, it creates another solution. So the reason why that doesn't work is because it neglects the case where a to the x is equal to, oh, I suppose that isn't ever going to work because a of x can never be negative. So normally, so let me if a equals 1, that obviously has one solution where a equals 1. If a squared is equal to 1, that has two solutions because it's, you've also introduced when a is equal to -1. And I was trying to apply that logic here and say if a to the x is equal to x, if I square both sides to get a to the 2x equals x squared, then that should introduce a new solution when a to the x equals -x. But that's never true because a to the x can never be negative. So I think a2 actually does work as well under that logic. And I think 3 is nonsense because you've squared the left-hand side and you multiplied the right-hand side by 2. It's just not the same thing. So I think it is 1 and 2, weirdly, and I think it's E. Okay, we're back to necessary and sufficient, so I'm going to get my little start and end points out. Hour left, making good time. Real non-zero constants. Necessary but not sufficient. Well, let me, again, I have to draw this out every time. So what does the relationship of necessary but not sufficient look like? Positive gradient and positive y-intercept. So we either have positive m and positive c, or we do not have positive m and positive c. And these conditions will either be true or false. And for it to be necessary, but not sufficient, it means it is the only thing that gets there, but it could go somewhere else. So I want a relationship that looks like this. If you want to arrive here, you have to, this thing has to be true, but that thing being true could lead to something else as well. Okay, so let's try and work this through. So I'm going to keep that there as a guide of this being the relationship that I want. Let's rearrange this. So by is equal to minus ax plus c. So y is equal to minus a over bx plus c. So obviously over b. So if this is positive and this is negative, if that is true, then this is true, but I do not have this relationship. That would be necessary and sufficient. Because there's no way that those things are both true. And like the only thing that can be true is that this gradient would be positive and intercept would be positive. I can't arrive at that would be necessary and sufficient, so it's not A. If C over B is negative, well, that can't be necessary. That doesn't arrive there. If A and C have opposite signs. That could be interesting. If it is true that A and C have opposite signs, then if B is negative, well, it basically means because B is the same thing, so these have the same signs, and you have minus A here and plus C here. If they have opposite signs, then suddenly what we know is that the gradient and the intercept would have the same sign. So they would either both be positive or both be negative. And so I think the answer is E, because that is the thing that has this relationship. Where the same thing being true could lead to a result of gradient and intercept both being positive or gradient and intercept not both being positive. So I'm going with E there. And again, every single time I'm going to draw this out because otherwise I can't do this logically. Okay, so going at question 8. Draws a triangle that is acute angled or obtuse angled, but not right angled. So the student counts the number of straight lines that divide the triangle into 2 triangles, at least one of which is right angled. I'm going to come back to 8. So I'm just going to make a note to come back to 8 because this just feels like I'm going to have to do some systematic mind trippy thing. I want to keep my momentum, and this would pause me. So going on to 9. So this is if then. Maybe I haven't gone into full detail about contrapositive or converse. So I think contrapositive is just counterexample. Well, the statement is not true. Because that can't possibly be true, because it's it's a pentagon. Well, let's think about it. So 360 over 5 gives me 72 is the exterior angle, which means in a regular pentagon, all the angles would be 108. I can also say that 180 times 3 gives me 540, which would be the sum of all the internal angles. So that's the sum that's for a regular pentagon. I would say it is entirely possible to come up to subtract 108 from 540 and then split those remaining 4 angles in such a way that they are not an arithmetic series. So the statement is definitely not true. Oh, okay, so what are they saying by contrapositive? I think contrapositive is just the negation from like the thing. So if okay, maybe I need to work on this logic. So that's a note to self for how I teach this coming week. So if at least one of the interior angles is that, then all angles form an arithmetic series. Okay. So what's the converse of that? If at least one of the angles is 108, then they do not form an arithmetic series. Well, you could choose to arrange them in a way that does. So I don't think the converse is true. What about like this contrapositive? All right, what I'm going to do, because I've got time, I just want to make sure I'm not misleading anyone. So TMUA contrapositive. Oh, well, I might try using my number line ideas. Just okay, so at least one. So okay, so we have none are, so all not. At least one is. At least one isn't. All are, which is the same as none are not. So I'm just going to lay that out. And in the real thing, I would probably write that number line and put it somewhere where I could see it, like for all of my negations. Let's try contrapositive. So what the statement is, if at least one is 108, the opposite of that is none are 108. Is it true that if none of the angles are 108, then at least I don't think the contrapositive has to, it can be true. If let me just check. Oh, this is good. Okay, so I think I found something. Let me go into this. So where is this explaining about contrapositives? Okay, so I'm going to bring this out here, and let's just have a little look at this, just to make sure we're conceptually understanding. Positive is also a lot here. Okay, so contrapositives. Statement and converse are not always the same thing. But what statements there are? Ah, okay. So this was going more into, if I go back up here to when I was explaining these. So if A, then B, the contrapositive is if not B, then not A. So considering the opposite relationship on this diagram. So here, I said B only if A. Okay, so let's see how this might apply here. So the contrapositive here would be so instead I'm going to use this logic. So these are really the two techniques that I have for this paper. You contain a 108 degrees, you have no 108s. Arithmetic series or not arithmetic series. And let me zoom in a little bit. So the statement they're making is this. So can we conclude that if it is not a series, so this is the contrapositive. If this leads to it not being a series, does not being a series mean that it's not 108? So if all the angles, if it's not true that all the angles form an arithmetic series, does that mean that one of the interior angles does that mean that none of the interior angles can be 108? And the answer is obviously not. It is entirely possible to get the angles together such that they do not form an arithmetic series, but also that you do include a 108. because that is certainly true, which means the contrapositive is not true. But also that is true. Like, this is just nonsense. None of this is true. So I'm gonna go for A. But I think the logic on that. Okay, so clearly I'm gonna need to tighten that up in my teaching, and hopefully I'll do a few more runs here to come up with systems. Once I've done the teaching and come up with a good way, I'll come back and do another run where I show how that works. Let me move on, though, in the interest of time. So, question 10. Also, realistically, what I should have done there is just sort of skipped it and guessed, demonstrating exam technique, but I just didn't want to actively mislead anyone. Here's an attempt to solve the inequality. Adding 4 to both sides is totally fine to do. If something's squared, this thing squared being less than 4. Well, that is true. That thing squared being less than 4 does mean no. No, the reason why line 3 doesn't work is because I don't think they've considered the negative case. No, but that is still included in there. So they haven't considered the case of well, actually, hold on. Let's make a substitution. Let's say z squared is less than 4. It is certainly true that z has to lie between -2 and 2. So I think they can say that. Because z squared minus 4 is, yeah, that would be -2. That would be 2. You would want it to be less than 4. Yeah, it is. That seems to be true. If and only if. Okay, well, line 3 to 4 looks bad. That's not correct, because it is entirely possible for this to be true, but this not to be true. So, for instance, this solution down here would include where x squared minus 1 is equal to -10, which is not included. So the error is definitely in line 4. That definitely doesn't follow on. So that's E. Um, 11. If then this. Okay, so if and only if and necessary sufficient, I'm just going to go to here. So we have 2k plus 1 is prime. We have 2k plus 1 is not prime. We have k is a power of 2. We have k is not a power of 2. So these kind of robust techniques that can apply in any situation. Well, not in any situation, but you know what I mean. Taken individually or equivalent to that. So what they're saying is this relationship. If this, then definitely that. They're not really making claims about this. So this could be a valid relationship, but they're definitely saying this start point only leads to this end point. Well, this is the most general mapping, which satisfies the statement. So it is statement 1 is not equivalent, because it is entirely possible for k to be power of 2 from this not being prime. Uh, 2k plus 1 is not prime, only if k, that's also not true, because again, there is this relationship between being not prime and k equaling 2 to the n, because the only in the general case, we would have everything going everywhere. The only restriction is we have is that this start point must end up at this end point. It didn't give us a restriction on the start point of it being not prime. So generally speaking, being not prime can end up at both endpoints. So 2 is not the case, because both 1 and 2 would require this cross pathing not to exist. A sufficient condition for 2 to be a power of k is that that's prime. No, that is sufficient. If this thing is prime, that is sufficient. That does get you there, and that only gets you there. Okay, so from my explanation of these start point endpoint mappings, 3 is equivalent, and 1 and 2 are not. So it's no, no, yes, which is G. Moving on to 12. Okay, we're back to necessary and sufficient. So again, I'm just going to do my mapping. It's my rigorous technique. Doesn't fail me, as long as I understand what it's asking for. So I would need to revise on some of the theory points about being contrapositive, but when I know what's happening, this is the technique. So the equation, this, has n distinct solutions in the range thingy. Okay, okay, so P is a real constant. Sufficient means it'll do. Sufficient means if I start here, I only end up here. So for the first case, either n is 3 or n is not equal to 3. And either P is bigger than 1 or P is less than or equal to 1. So what they are saying is for sufficiency, that ends up there and only there. And that is the most general mapping that could exist. For the second one, what mapping are they talking about? So n equals 7 is the result. That's the endpoint, and we're considering start points. So these are what we're considering, or P is less than or equal to -1, or P is bigger than or equal to 1. And if we want this only if that, the only way to arrive at n equals 7 is from this start point. So this endpoint, but I could do that. So these are the two things we're considering. Are these true if this is true? So n is sufficient for P bigger than 1. And distinct solutions in the range. Well, let me actually try and solve this now. And then I can just scroll up to the mappings as required. So I'm definitely not going to divide by sine x, because then I would lose solutions. Instead, I'm going to subtract the p squared sine x across. And I'm going to factor out the sine x. So I either have sine x equals 0 or cos x is equal to plus minus p. If p is bigger than 1, then this has no solutions. So you're only looking for sine x equaling 0, which does have 3 solutions. Is it true that if n equals 3, that can only result in p being bigger than 1? Well, we know from this that this has 3, so if n equals 3, then it does mean that this has no solutions, which does mean if p was not bigger than or equal to 1, then this would definitely have some zeros in it, so I think that is true. And then for the second point, for p being less than or equal to 1, then I would get 4 solutions. So that would bring me to 7. And the only way to get 7, I think that is true. I think the only way to get 7 solutions is for this to be true, because only that way, because you have the 3 locked in guaranteed from the sin x in this range. But the only way to get to 7 is if this is true, so that you can introduce the other 4 from the cos bit. So I think both of them are true. I'm going to go for D. Sufficient condition. So again, so sufficient means it will do. Sufficient, again, I'm going to draw my sufficiency curve, but I'm going to draw it generally. So going from A to B being true, false, true, false. For sufficiency, this gets me there. It's the only, but something else can get me there as well. This is the sufficiency mapping. So if I start at A, do I definitely end up at B and nowhere else? For exactly 3 of the other 4. So if I have, for one of these statements, if I start here, I definitely end up at 3 of the other statements with no other possible endpoint. Now, let's consider it one by one. If it is A, I can end up somewhere other than B. I can end up somewhere other than C. Immediately, it cannot be A. If it is B, I do end up at A. I do end up at C. I do end up at D. I do end up at E. So if it was B, it would be all 4. So the question is, where do I end up? So for C, if this is true, I do end up at A. I do not necessarily end up at B. I do end up at D. I do end up at E. So I think the answer is C so far, but I'm going to check the others. If I start at D, I do not necessarily end up at A. I could end up somewhere other than A. I could end up somewhere other than B, so not D. I could end up somewhere other than A. I could end up somewhere B. Okay, the answer is C. Okay. More if-thens, so I'm going to keep on mapping. You can see why I introduced this before the run. It's like so critical to my personal understanding of how to approach these questions. If then. Okay, well, let me rewrite all of these in y equals mx plus c form. So we have y equals minus a over bx minus c over b. For the second one, we have y equals minus b over cx minus a over c. For the third one, we have y equals minus c over ay minus b over c. Which of the following is correct? If 2 of the lines are parallel, that means 2 of the gradients are equal. Does that mean that the third gradient has to be equal as well? Without loss of generality, we can try and set those to be equal to each other. If a over b equals b over c, well, you could, in theory, have a situation where if a was 1 and b is 2, and c was 4, then this gradient would not be the same. So that does not have to follow. So a is not true. So if 2 of the lines are parallel, then the third is a perpendicular. So that would be, so for instance, well, let's take the 1 over 2 case again. 1, 2, 2, 4. And the gradient would be negative a half. But then this would be -4, which is not perpendicular, so B, just the counterexample, B can't be correct. The third is parallel to y equals x, so has a gradient of 1. Again, we just did an example where A is 1, B is 2, C is 4. That is not parallel to that. It's also not perpendicular to that, so I don't think any of these are true because I come up with counterexamples for all of A to D, just from 1, 2, 4. So if two of the lines are perpendicular now, so if, for instance, if without loss of generality again, let's say that these are perpendicular, which means that minus A over B is equal to C over B. That would mean that A, because B cannot be 0, it does mean, well, let me do this rigorously. BC plus AC, which I can factorize out, sorry, plus AB. I can factorize out a B. But B cannot equal 0 because then these gradients would be infinite. So I know that A would have to equal minus C, which you could probably have done intuitively, but I just wanted to be rigorous. And if A was equal to minus C, then this gradient would be 1. So F is correct. Okay. Moving on to 15. Ugh. Okay. Oh no, it's not too bad. So the base 2 number. Ugh. How much time have I got left? Half an hour. Okay. Oh, that is so interesting. I know how I would do recurring. Ah. Oh, that's fascinating. So, okay, how would I, okay, let me consider what I do know. So let me say, for instance, how would I do 0.01 recurring in decimal, in base 10? I would say x is equal to that. The recurrence is right up to the thing. I would then multiply by my base squared because there are 2 digits in the recurrence. Base squared would be 100, and that would get me 1.01 recurring. I would then subtract and get 99x is equal to 1, and x is equal to 1 over 99. So invoking what I know, let's see how that would apply here. So instead of x was equal to 0.0011, the recurrence is right up to the decimal, so I'm fine. There are 4 digits in it, so I have to multiply by the base to the 4. 2 to the 4 is 16. So I know 16x is equal to 11.0011 recurring, which means that if I subtract them, that 15x is equal to 11, and so x is equal to 11 over 15, which is not a solution. No, I was so onto something. Oh, wait. Would it be 11? Would it be 11? Would that move the decimal, or would that do something else? Oh, well, I suppose they've given me an example. Oh, why don't I do this instead as a geometric series of sorts? So I know I'm going to have 2 to the minus 2, 2 to the minus 3. Sorry, 2 to the minus 1, 2 to the minus 3. 1 over 2 to the 4. 5, 6, 7, 8, 9, 10, 11, 12. So we definitely get a geometric series out of this. So we've got that. So that is 1 over 8 plus 1 over 16. But then that whole thing, it's plus that times 1 over 16, which is 1 over 2 to the 4, times the same thing. And then that's 2 to the 8. So 1 over 16 squared of the same thing. So our A value is going to be 216. So our A value is 3 over 16. And our R value is 1 over 16. And we want the sum to infinity. So that would be A over 1 minus R, which is 3 over 16. In fact, let me just multiply top and bottom by 16 straight out. 3 over 16 minus 1 is 3 over 15 is 1/5. So I'm going to say B and lock that in. Okay, so for 16, I really thought the first solution was going to be good. All right. Highest common factor of A and B is 7. Which of the following statements must be true? And there's a Fibonacci sequence. So previous gives you next. So we have A, B, A plus B, A plus 2B, 2A plus 3B, 3A plus 5B. So we can see this is going to be a Fibonacci series where the coefficient of B is one number ahead of the coefficient of A. Well, if the highest common factor of A and B is 7, it means that 7 is a common factor of A and B. And we can see that this u to the whatever is going to have integer coefficients of A and B. So it will be a multiple of 7. One is definitely true. If u1 is not a factor of u2, so if if A is not a factor of B, then A is not a factor of any other thing. That does not have to be true. So for instance, let's take the case where A is equal to 2 and B is equal to 3. Then it is certainly true that 2 is not a factor of 3, but here I would have 2 plus 6, which is 8, and 2 is a factor of this. So 2 is not necessarily true. The highest common factor of u1 and u5. 1, 2, 3, 4, 5. Does that have to be true? Well, let me write A is 7k and B is 7n, where n and k have no prime factors in common. That would be 14k plus 21n, which would just be 7 into that. Can I construct? Oh, wait, my counterexample didn't work because the highest common factor should have been 7. If I multiply them both by 7, would that have worked? So if I made that 14 and 21, I still think it would have worked here if I just multiplied everything by 7. It would have got me 56. Yeah, it would have worked. Is that true? Oh, what's my time? I've got 20 minutes left. So they definitely get harder. I may have started at the back. No, it's... Okay, so... Because my pacing's a little off. Is the highest common factor? Can the highest common factor be anything else? Can that have a factor of 2 in it, for instance, to make it 14? highest common factor. So if A is equal to 2, if A is even, okay, let's try this. If A is even, it just says the highest common factor of A and B is 7. Oh, but then that means, okay, so that means that B would have to be odd, because otherwise 14 would be a common factor. And even plus odd is odd. So the highest common factor would, well, certainly not be 14. Let's try this the other way around. What if A was 21 and B was 14? Then that would be 42 plus 42 is 84, and 21. And the highest common factor would not be 7, so 3 does not have to be true. So 1 is the only one that has to be true, and that's B. Okay. 17. By the way, the my reasoning there was to force a situation. I was like, okay, well, if B had a factor of 2 in it and this had a factor of 3 in it. So in other words, if these if it could be a factor by virtue of the coefficient rather than the number itself, might be a bit difficult to explain. But let me move on to 17. Ceiling of x written by that is defined as rounding up to the nearest integer. Rounding up always, not to the closest. But you're rounding up. What is the... Okay, well, what this means is 0 goes to 0. Okay, so this finds the area. So that's 2. Let me graph this. Just to get a sense of what's happening. So from 2 to the 0, it's 1. So that adds 1 there. That's 1. Then as soon as you move off 1, it goes to 2, between 0 and 1. Then it goes up to 4 between 1 and 2. Then it goes up, so that's 2, 2 squared, 2 cubed. Then it goes up to 8 between 2 and 3. So this is going to be, we're going to be adding up all of these rectangles of width 1 and height 2 to the n. So that is going to be the sum of 2 and 2 squared and 2 cubed, etc., ending with 2 to the 99. So A is going to be equal to 2. R is going to be equal to 2. The number of terms is 99. The sum of those 99 terms, sorry, it's the sum of it's the sum of 99 rectangles, and that's going to matter with these powers. So the sum of the 99 rectangles is equal to A r to the 99 rectangles minus 1 all over r minus 1, which is obviously just 1, and r is equal to 2, which is 2 to the 100 minus 2, which is f. Okay. Moving on. We got more if and only if. Okay, just so we can see a bit better. 18. For distinct real roots, if and only if, which of the following conditions is satisfied? So in other words, if I start at this condition, do I definitely end up with this thing being true? If this thing is true, can it only have arrived from this thing being true? So if and only if, in terms of the mapping, just looks like this. If I start here, I definitely end up here. If I end up here, I can only have started from here. Has four distinct. Well, we know if C. Okay, this is a quartic. How does any quartic have four distinct real roots? Well, it's also, we know the graph is going to look like this. So the only way is if the turning points lie on either sides of the x-axis. So if I differentiate this and set it to 0, let's see what happens. So 4x and cubed and 2bx would equal 0. So x into 4x squared, well, I'll take a 2 out actually. So 2x squared plus b would equal 0. Well, first of all, it has to have 3 turning points. If it only had 1 turning point, then it can only ever go through twice. So it wouldn't have 4 distinct real roots. So we need there to be solutions to this. Which means that b has to be negative. So we can already eliminate e. Or alternatively, yes. Okay, so I'm seeing stealth quadratic as well. So we know b has to be negative. So I've got that from that. That might still be useful. What else do I know? I can call that. I can say that the solution. So x squared. So the solution is on the quadratic. Let me be more explicit. We're going to say that y is equal to x squared and then substitute that in to say that y squared and by and c is 0. So I would definitely need to have. What I would need to have is 2 non-zero solutions to y. 2 distinct non-zero solutions to y. So when do I get 2 distinct solutions? When b squared minus 4ac is bigger than 0. So it is definitely true that that is true. That is not sufficient, though. That does not get me there because I also need, so I need this, I definitely need this to be true, but I need more than that. I also need that the solutions that gets have to be positive. And the solutions I get are minus b plus minus square root b squared minus 4ac, where a is 1. So again, I certainly need this to be positive. So what do I need? I need b squared bigger than 4c. I need minus b over 2 to be bigger than 0, which means that I need b to be less than 0. So those two things need to be true. B squared okay, so is it certainly not B? It's certainly not F. I don't think it's A because that's not sufficient. That gives me 2 solutions for Y, but if Y was negative, then that wouldn't work. So what is the condition now on these to be positive? Okay, let's think about that. What I would need for this to be positive is this would be, let's think about what the roots would be there on like some sort of number line. What's my time left? Not a huge amount of time. So I would have, I want it to be something like this, where this would be minus b over 2, and it would then go this square root over 2 in that direction. So I would need for that square root to be less in value than the minus b over 2, the magnitude of that. So I would need the square root of b squared minus 4c over 2 to be less than the b over 2. If c was equal to 0, they would be equal. I need this thing to be smaller, so I need the thing in the square root to be smaller in size. So I need c to be positive such that this thing is less than the b. So I need c positive as well. I'll add that to my list of so I need that. I need c positive. So I need c positive. And b has to be negative. So I'm going to say the only thing that satisfies that is d. Yes. 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 Because if I follow that through from here, yeah, it's d. It's d. So b doesn't just have to be less than 0. From here, it has to be square both sides. B squared has to be bigger than that. So b has to be less than minus 2 root c, or b has to be bigger than 2 root c. This can't be true because c has to be positive. So, and that's, yeah, it's d. It's d. It just is d. I've only got 10 minutes left, and these questions have gotten slower. My pacing I need to pick up clearly for the real thing. So again, this is my first blind solve, so this sets a baseline. So what I do with these is I kind of don't show you perfect right off the start. I show you where you start and how you can make adjustments to your process to improve. So I kind of put myself in the student role rather than the teacher role. So here, 19, non-constant polynomial, g of x is x times the d, okay. So for 19, non-constant polynomial, m real values of x. So I know that if that is 0 for exactly m real values of x, I don't know for certain. Okay, so what I'm going to have to do is just come up with examples for each case. Is it possible that m is less than n? So let me come up with some possible examples for what. Okay, so if this was f of x, for instance, 3, then it would have 2 turning points. So let's try one where that's 0. Let's try one where none are 0. Let's try one where there's like a turning point as a solution as well, which may or may not be 0. Is it possible that m is equal to n? Let's just try that first of all. So in this second case, m would be equal to 3. And let's say that 0 was off the maximum as well. Then there would be, for g of x equaling 0, that would be when f dash of x equals 0. So that would be 1, 2, and introducing an x equals 0 root, so I can get n equals 3 from that. So 2 is definitely possible. Is it possible that m is bigger than n? Let's try this case. M is equal to 3. Uh, g of x, you would have 2 from that, but it would also have an equals. Okay, so let's try instead the situation where 0 is at the turning point. So in this case, you'd have 2 solutions from that, but that would be repeated root on 0, so n would have 2. So 3 is definitely possible. Is it possible? So here, this has 2 solutions. And let's put 0 here. So here, m would be equal to 2. And n, well, I would have 1, 2, and 3 from the turning point. And 2 from the turning points and 3 from the 0. So all are possible. And I'm going to go for h. I have 5 minutes left. I'm hoping that paper 1 goes a bit faster. So we have more if and only if. And that looks really ugly. Which of the following statements must be true? Must be true. F of x squared. Okay, well, what do I know about function of the modulus? I know that what you do is you draw it in the positive case and then flip it. So let's say that was f of x. So they're only different when x is negative. So whenever x is positive, these will be exactly the same because f dash of x, sorry, a function of the modulus will equal the function of x when x is positive. So these would be the same thing. You would get 0. Well, 1 is not true. Oh no, 1 is true. Hold on. It is okay. Let's try if and only logic. So it is certainly true that if 0 is less than p, then I is that the only way to get I is less than 0? The integral equaling 0? I don't think it is because of the square. Yeah, so let's say it's the function is x cubed. That would look like this. And then the integral would look like this, but when you square it, it would map onto itself. So it is not only true. 1 is not true. It's decreasing for all x only if the integral is negative. Can I find a case where the integral is negative and it's not increasing for all x? I think 3 is correct. In the interest of time, because I've only got 2 minutes left and I have another question to go to. So I know 3 is right. I know 1 is wrong. I'm going to guess 3 and 2 only, just because now we're into the end game of the paper. I need to make sure I submit answers to at least increase my chances of getting something right. I know I haven't done this. So let me go back and do 8 with 2 minutes left on the clock. Let's draw an acute angle triangle, and let's draw an obtuse angle triangle generically. If it's obtuse, I can draw one perpendicular to there. I can draw one perpendicular to there. I can draw one perpendicular to there, but that wouldn't be two triangles, so it'd have to be from... Yeah, I could draw one from this corner perpendicular to all three. So I can definitely draw one with three. I can draw one from here perpendicular. At least one of which is right angled. I think you can always draw one from a corner to the opposite side, can't you? And if it's obtuse, I can always draw from that obtuse angle. I can always draw three. I think it's three only. So I'm going to go for D, and I'm actually going to call it there because I'm not going to get the other one in 35 seconds. All right. So let me start marking this up. I'm not going to give myself spoilers, but I'm only going to look at pass 2. Let's see how I scored. All right, so that was when I was going through the working. So 2F, wait, where's 1? H, F, C, G, A. So I got 5 wrong. That's annoying because it's necessary and sufficient. Okay, so I got something wrong in my integral then, clearly. That's not right, is it? Let me get rid of that. 5A, it's necessary and sufficient. All right, let me get... I should get solutions for these. TMUA. Let's get question 5. Okay, so what are they arguing here? Oh, of course. Oh, okay. It would have been correct, but here was my mistake. So in my execution, I said that this happens every pi, but it equals 1 only every 2 pi. So it was right that k is equal to n pi. So that is why actually this path would not have existed. And it was necessary and sufficient. All right, that makes sense. That was just a small execution error. Okay, so then going through, I said E, it was F. So getting more wrong, the early stages of doing the TMUA runs. And what you'll see is in my runs, I will improve, and I'll show you how I'm improving, putting myself in your shoes. F, 6F. Okay, so 1 and 3 only. Did I? Oh, no, I just fundamentally misunderstood this then. We introduce a new set of the solutions, plus or minus A. Yeah, I considered the case where x is less than negative. Oh, I forgot the case where x is negative, though. Okay, so I should have followed that through a bit closer. Okay, so I just didn't follow the logic all the way through. When x is negative, I forgot when x is negative, that becomes positive, because, of course, I said a of x always had to be positive, but then I argued that this always had to be negative, which was not the case when x was negative. And this I'm surprised by. This I just discounted immediately as having needing to have the same number of solutions. Oh, I suppose, of course, If you just do a sort of classic, if you replace x with y and substitute that in, say y is equal to 2x, it's just the same. That was bad on my part. That was conceptual. So the idea here is this I can substitute for anything. So as long as if this equals that, then I can replace that with anything I want, and the equation still holds, including the case where that is 2x. So that was just poor form. 7e, 8 I skipped. 9 I said A again. Not my best work. So why not? What can I learn from this? Oh, this was again me conceptually not understanding some of the conceptual stuff. So 9. So the sum is 540. The mean is 108. You can form an arithmetic. You can form one which doesn't form an arithmetic series. Okay, so the actual answer was 3 only. The converse was apparently true. So the contrapositive of a statement always does the same truth as the statement itself, okay? So the converse is okay, see, I misunderstood. Okay. So a contrapositive always has the same truth as the statement. The converse I got wrong. The converse would actually been the thing in reverse. So if all the interior angles form an arithmetic series, then at least one of the interior angles is 108. That's the one that did have to be true. Okay, so the converse is not a sort of negation thing. It's just swapping around the if and then. Okay, so in future runs, I'm going to clarify that before I do a run. So that was more I can do from the specimen or the specification to get into that conceptually. Good to know. 10. Let's see if this kept going badly. It did. 10 was A. So improvements to be made. Here's an attempt to solve the inequality. Oh, the argument is completely correct. Oh, yeah. Okay, I see what happened there. The issue was anything squared has to be positive. No, but then that could. Oh, I see. Okay. So let's sketch x squared minus 1. It is already inherently limited in that. Just by its very nature, it is already, just by the range of the function, that is inherently true. So I don't need to specify that. Just it being itself satisfies the left-hand equation. So the only thing I have to constrain is this bit on the right. Okay. In fact, I should really make a note of what I'm getting right and what I'm getting wrong here. So it doesn't look like I'll have time to complete paper 1 as well. So this will just be like a warm-up for how to go through the paper 2 more conceptually. Right, so paper 2H. So it was H, F, C, G. What did I get wrong? I got 5 wrong. I got 6 wrong. 7. We haven't even talked about 8 yet. I got 9 wrong. Got 10 wrong. This is not great work for me. But it's all right. Okay, so that pivots how I'm going to do this series then. So then my challenge is, do I get full marks in this? Can I get myself there? So 10 I got wrong. 11G, 12D. Okay. Using if-then language. So if n equals 3, then p is greater than 1. True. And if n equals 7, then this is true. So they're arguing the equation we rearranged is that. Certainly, that's exactly what I did. So sine equals 0 gives you 3 solutions. And cos equals that. Oh, I didn't consider the p equals 0 case, only giving 2. Sneaky that. Yeah. Certainly has 4 for when for the everything in that range except for when p equals 0. Okay. Okay. So I got 12 wrong. Uh, 13, I said C. Yep, I got that right. 14F is correct. 15B is correct. 16B, 17F. You see, weirdly, as I moved through the paper, I ended up doing better. 18D, 19, I said G, H. 20, I said D, but that was a guess. Just from, let me look at 20. G was a guess. It was D. So 2 was in fact not correct. Oh, sorry, I should have guessed that. It would have been too restrictive. I should, in general, if you're gonna make a guess, say that the restriction is not true. But let's have a look at how it should have been done. So we're gonna go to question 20. Okay, so I was correct in my assessment of 1. Does what they're saying make sense? So for negative values of x, close to x equals 0. This is bigger, but once x gets to that point, this is complicated. I prefer my solution. So what did I do? So if you can come up with a single counterexample, that's fine. So if p is less than 1, so once you dip into the negative, I came up with a case of f of x equaling x cubed. Then I equaled 0, even when p was negative. So yeah, coming up with a single counterexample, I prefer my explanation of that. Let's take 2. They just took as negative straight lines, so it's decreasing for all x. So again, just coming up with a counterexample. So the easiest thing that is decreasing for all x is just a straight line with negative gradient. And doing it in such a way here the integral is 0. So it's not bigger than 0. Oh, sorry, it's not less than 0. It equals 0 for the straight line. Okay. So that was complicated. Now let me go back. An 8, I randomly guessed D, but I got that right. And probably for the same reasons. So I'll write 20 down. It's one that I got wrong. Okay, so 8. Let's see if they drew it out the way I drew it out. Yep, you can just draw a line from each vertex to its opposite side at a right angle in the acute triangle. And for an obtuse, yeah, you from that angle just to the other 3 sides. Yeah, they did exactly what I did. Okay. So I got only 14 out of 20 on that, which is not up to my usual standard. So what I would do in this situation, I'm going to keep this up just because I'm not afraid to be seen to be failing in public, because I think it's worth demonstrating you don't start it perfect. You've got to put the work in to get there. So what work do I need to put in to get to the paper 2 standard? This was an execution error. I would have been fine. This was just not considering it as deeply. I should have more deeply considered the negative x case, and I should have more deeply considered change of variable to call x 2x. So that was just conceptual. That was a problem of not thinking well enough about it. For 9, okay, I'm going to go away and do more work on, because I've got good stuff going for necessary and sufficient, like and for the negation logic. That I do well. This is clearly something I have to add. What I will say is I haven't seen contrapositive come up in the work that I did for people for the October series. I didn't see contrapositive come up too much, but clearly I need to spend a little bit more time on that. So next time I do a TMUA paper, I'm going to go through the spec and really nail these. What went wrong in 10? Okay, on paper this looked wrong, but I should have just more deeply considered it. I should have sketched it out and seen, because I just looked at that at face value and went, that has to be wrong, and moved on. I should have more deeply considered that. And again, I should have more deeply considered this. So that seems to be a paper 2 thing, like coming up with every possible, like realizing all of your assumptions and trying to come up with traps, trying to come up with ideas of where is this idea that I'm having, where is it not true? Have I considered all the possible cases here? I had a good run until 20 where, again, just time ran out. And things like this, coming up with counter, especially for the only ifs, is coming up with a single counter example is the way to go there. I just ran out of time, though. And that's the other issue, is I assumed I would have more time. I went, oh, 20 questions in 75 minutes. That's a breeze. That's absolutely fine. But what I didn't consider is putting in that consideration time means that things take longer than you think they're going to. So thinking more deeply, like I was still probably in ESAT brain where I was like, oh, whatever it is on the surface is going to be what it is. Not the case. I'm going to have to consider things more deeply, think much more like a pure mathematician. Clearly the work I've done has gotten me so far. I just need to do a little bit more work thinking about counter examples to my own logic that I'm putting forward. So that gives me something to do. I've got a session in an hour. That's not going to be enough time to run through all of paper 1. And especially, I would rather put in these changes. Paper 1 is a bit more standard. It doesn't have a lot of this much more like hardcore logic to it. But I would want to have that be my first dip into doing a paper run myself, front to back. I would want to think about changes I want to make to my process, doing a bit more conceptual work from the syllabus, cementing those skills independently of the paper, and get myself in the right mindset, because clearly I wasn't thinking about everything I needed to think about. So I need to go ahead, do some work, improve my conceptual understanding, and improve my sort of front end mental attitude and sort of approach to the paper, thinking about improving my pace, um, things like that. Um, so yeah, okay. So I've got a plan. I've got a personal plan, and everything I'm doing now is a demonstration of what you can be doing on your end. So to doing a paper, what do I understand? What do I not understand? Go away doing that work, and I'm going to come back hopefully with a better approach that's going to yield better results, and I'm going to see my results track up. I also want to make sure everything's okay with paper one next time I do a TMUA run. So I'll just give myself a bit more time to make sure I can get all of that done. So hopefully I've made some instructive mistakes. So even it's instructive when I get it right. Hopefully it's also instructive when I get it wrong. Because I imagine a lot of people are making similar types of mistake, and this logic is very different than what you do in the classroom. So it just takes some time to get there. And this is just me saying, yeah, it's not just you. Yeah, it's me too. It's just hard. Because I'm very much in the brain of syllabus material. I teach it all the time. That's where my brain sits. TMUA is different. And so you've got to just sort of stretch your brain to get into that new zone. All right. So I know what I'm going to do on my end. I'm going to leave it there. I'm going to put together a schedule for the ESAT runs and for the interview technique. And hopefully I'll just get more things together. I want to set up like a sort of website, actually get like a profile picture and a banner, and kind of just make things a bit more formal. Maybe get like a rigorous schedule, which I put on a community tab, so you know what streams are going to come up when, so you know you can kind of arrange and tune in if you want to be there to see something specific. Cool. So that's the plan. All right, I'll leave it there. Yeah, it's been 2 hours and 10 minutes. I think that's quite enough. No one needs a second paper from that. Right. So go off, work hard, have fun. I'll see you next time.